Greetings. In my previous video, we managed to solve a problem for the basic Rankine cycle, which is used for steam turbines. Now, there are alternatives to the basic Rankine cycle, and there are additions to it, which in this video and the next ones, we shall try to solve also problems for those additions. Now, this is the basic Rankine cycle that we discussed. The cycle was from 1 to 2, where there was a pump. Then there was from 2 to 3, where there was a boiler. And then it was from 3 to 4, where there was a turbine. There are two problems with this cycle. First was that the heat addition was from point 2 to point 3, and point 2 had a temperature of 48 degrees centigrade, point 3 had 800 degrees centigrade, and the average or equivalent heat addition temperature, which we could use for the ideal Carnot cycle, would be fairly low. If we could add heat at higher temperatures, that would greatly help our Carnot cycle efficiency, and also it would help our real cycle efficiency. The other point was that point 4 had a quality of 90%. This means that in many end stages of the turbine, there would be water droplets, and they would hit the blades and cause erosion and cause pitting. So the way to solve this problem is through a reheat. What they do is that they take the steam at some stage out of the turbine, bring it to the boiler, and then expand it in a different turbine. So, in fact, our problem would look like this in a real diagram. Look, if this is the boiler, if this is our boiler, the flow out of the pump would come to the boiler, heat, and get out. It would enter a turbine, which is the high pressure turbine. This is our turbine, high pressure turbine, and the flow out of that turbine would come into the boiler, would return to the boiler, get some further heat, and heat up to the, say, the turbine entry temperature. If we can make blades that can stand, say, 800 degrees C, then there is no reason why we shouldn't repeat that practice. And then they would return to a low pressure turbine. This is another turbine, which usually these turbines run on the same shaft. They don't have different shafts. So the outcome comes to a condenser. This is a condenser, and the outgoing flow from the condenser goes to a pump, and then the pump would pump the fluid back to the boiler, and this would be our diagram. Now, what the problem is telling us is this. That is, it is telling us that the flow from the first turbine exits this turbine at 630 degrees C. So it would go out perhaps something like here. It is the temperature here is 630 degrees C and is heated in the boiler again to 800 degrees C. And then it's expanded in the next turbine. So we would, if uh, the first turbine was an isentropic turbine, we would get to point 5. We shall investigate that later on. If with this exit temperature, 630 degrees C, if the first turbine is isentropic or not. And then, but in reality, the point we're given is point 6, where the temperature is 630 degrees C. It is heated up to point 7, where the temperature is 800 degrees C, and then it's expanded to point 8. Still, we are not sure if this point is inside the saturation dome or it's outside, but we shall investigate it very shortly. Well, now, uh, the first step to solve such problems and all the cycle problems is to find the points, find the properties. That's a very important first step, and it's a very time consuming first step that we should do one by one. If I try to put these numbers on this figure, this is point 1, which is entry to the pump. This is point 2, where the pump is the pump exit. This is point 3, is the boiler exit and entry to the high pressure turbine. This is point 6. The point 5 is for ideal turbine, and we don't know if we have it or not, but we know that we have a point 6 where the fluid goes out of the turbine into the boiler again, and at point 7 it goes out and enters the second turbine, and out of the second turbine is point 8 and then enters that condenser. So these numbers correspond with numbers on a real diagram. Okay, now let's see which properties we have and which properties we don't have. Now, for point 5, we don't know if we have it or not. For point 5, we don't have it certainly, but we don't know if it is any different from point 6 or not. We have to check that certainly. We know that the pressure is 4,000 pascals. The problem tells us that the intermediate pressure is 4,000 kilopascal. Is temperature we don't know. We shall investigate. This enthalpy we don't know. What we know is that it's the exit point of an isentropic turbine. So the entropy would be 7.408. So with the knowledge of pressure and entropy, we could easily go to the tables or to a software and understand what the property for point 5 is. And the result would be 615 would be the temperature, and 3709.4 would be the enthalpy, and 6 the temperature, since the temperature at point 5 is less than temperature at point 6, therefore we know that we don't have a isentropic turbine. At point 5, the temperature is 615 degrees C. Of course, this diagram is not up to scale since the temperature here in the critical point is 373 degrees C. And so this point should be lower than this one, and these lines should have a much sharper slope. But with the knowledge of that, we would continue our solution. Point six is on a 4,000 kilopascal line, so we know the pressure. We also know the temperature, which the problem tells us it is 630. And going to superheat tables, we could easily read enthalpy and entropy. The enthalpy would be 3743.9 kilojoule per kilogram, and the entropy would be 4.6, 7.4482 kilojoule per kilogram Kelvin. Now, point 7 is also known. We have a lot of information about point 7 since we know its pressure is 4,000 Pascal. Its temperature is 800 degrees C, and therefore tables would tell us all properties, and the properties are 4142, 4142.3 kilojoule per kilogram, that's the enthalpy, and 7.85 to 3 kilojoule per kilogram Kelvin is the entropy of point 7. The final point we have to find out where it is and what its properties are is point 8. And what we know about point 8 is that the pressure is 10 kilopascal. The pressure here was 10 megapascal. This line was 4 megapascal, and this line is 10 kilopascal, and its entropy is identical with entropy at point 7. So for point 8, we know that pressure is 10. The pressure is 10 kilopascal, and entropy is 7.8523. Well, a very easy way to check where we stand is returning to the tables, property tables, and see at 10 kilopascal, what the saturation entropy is. And the saturated vapor entropy is 8.1488. So we learned that since the entropy of point 8 is smaller than the saturation vapor, the entropy of saturated vapor, therefore this point is still in the saturated range and is not superheat. So what we do to calculate the other properties for this point, of course, for point 8, we know that the temperature is the saturation temperature, so the temperature is 45.81, but the quality we don't know, and the way to calculate it is very simple. We know that x8 equals S8 minus SF divided by SFG. And putting numbers into this equation, it would be 7.8523 minus 0.6492 and divided by 7.4996. And the outcome of this would give us x8 to be 0.96. And using this value to calculate enthalpy of point 8 is H8 is 2489.3. How did we calculate that? This was HF plus XHFG, which was from the values that we know from the table. HF is 191.81 and plus 0.96 times HFG, which is 2392.1, and the outcome would be 2489.3, and we could insert this value into our table to fill just all the properties. It would be 2489, 2489.3, and the quality is 0.96, which is still somehow high, but much better than the quality of 0.9. So one or two last stages of the steam turbine would have water droplets in it. But this is the properties as we have calculated. Our governing equations are very similar to what we used for the basic Rankine cycle. I mean, all elements are steady state, and that's how we calculate them. So inlet and outlet mass flows are equal. If we have heat transfer, we have two types of instruments. Either there is a pump or turbine where there is work but no heat transfer, and the other one are boiler or condenser where there is heat transfer but no work. So the story is very simple. This is our equation. We either have Q and not W, or alternatively, we have W and not Q. So, and if it is isentropic, then entropies remain the same between inlet and output. So equations are very much similar to what we had, and this practice continues. So the first step that we need to take is to calculate the efficiency of our turbine. You see, the turbine, the real turbine, does not follow the process 3.5, but it follows process 3.6, and therefore we can define and calculate turbine efficiency. Turbine efficiency is the work of the real turbine, which is H3 minus H6, divided by the work by an ideal turbine, which is H3 minus H5. And we have all the values. That's the good point of calculating all values to start with. And it is 4114.8 minus 3743.9 and divided by 4114.8 minus 3709.4, and the outcome is 0.917, which means that our turbine has an efficiency of 91.7%, which is quite normal for axial flow turbines, and turbines in power plants usually have the same efficiency. Now, after this step, the step we have to take, and we take, is to calculate the cycle efficiency now. For the new cycle, for the reheat cycle, we have two heating processes and two turbines. So if we write the cycle efficiency for the cycle is first, nominator is what we have got, and there are two turbines. One is high pressure turbines, and its work is H3 minus H6, and the other turbine is low pressure turbine, and its work is H7 minus H8. And these are the two turbines, and there are two stages for heat transfer. One is the original heat transfer from 2 to 3, and the other one is the reheat heat transfer from 6 to 7. So it would be H3 minus H2 and plus H7 minus H6, and inserting values into this equation, it would be 4114.8 minus 3743.9 and plus 4142.3 minus 2489.3, and these are the works by both turbines, and the heat added to the cycle are 4114.8 minus H2, which is 201.9, plus 41 H7 4142.3 minus 3743.9, and the outcome for the efficiency of the whole cycle is eta equals 0.469 or 46.9%, which is a good value, which is a good addition to the previous original cycle, which is the efficiency of the original cycle efficiency was 44.9%. So adding this reheat has in fact increased our total efficiency. If you remember, in the gas turbines, this didn't happen. Adding reheat reduced efficiency, since in the gas turbine, the reheat part didn't expand to lower temperatures. So it was just a cycle up here, and it had a lower efficiency, and therefore it reduced efficiency of the original cycle. But here we have a cycle with high temperature as high as the original cycle, and heat addition is done to it at the very high temperatures, and its lower temperature is also the same as before. So we expect this new added cycle to have a higher efficiency, and therefore it should be able to increase the whole cycle efficiency, which we see here in the result that it has done it. And it has increased the efficiency from 44.9 to 46.9, which is a 2% added efficiency. Now, the final step in this solution is to calculate work of the total work of the cycle. And the total work is m dot, of course, time W for the high pressure turbine plus W for the low pressure turbine minus the same m dot times the pump work. So it is the turbine work, total turbine work, and the total pump work. It's both of them which we have to take care. Therefore, W dot would be 113.836, which we're assuming the same mass flow rate as the previous example, just to see that if the reheat has increased our total work or not. And we expect it to happen. It is times 4114.8 minus 3743.9 plus the work of the other turbine, the second turbine, it is 4142.3 minus 2489.3. This is the works of both turbines, and minus the work by the pump, which was 10.09, which was 10.09, and this was the work of the other turbine. And these are all kilojoules and kilograms inside the brackets, multiplied by the mass flow rate, and the final work of the whole cycle would be 229,244 kilowatt, or W dot would be 229.244 megawatts. If you remember, the work for the previous example for the original cycle was only 200 megawatts. So the addition of the reheat cycle has basically increased both our efficiency and also our work. So we have got more work, and all the work is more efficient. This is a good addition to the cycle. Well, thank you very much for watching, and cheers.